Hello everyone, welcome back to lecture 13 of Spatial Statistics and Spatial Econometrics. In this lecture, we will study the tools that are needed to apply the theory of a variogram on a given sample data set. When I say that we will apply the theory or mobilize the theory of a variogram, I am including the theory of spatial stationarity. That is, when and how can we decide whether or not a given spatial domain is stationary, right? After that, we are also including the idea or the concept of spatial contiguity. What is spatial contiguity and how do we measure it? What is the utility of spatial contiguity? Remember, when data are spatially contiguous, that is to say that values at locations which are spatially proximate or located closer to each other tend to be more similar usually than values at locations that are located farther apart, right? Now, this phenomenon, which is known as spatial contiguity, is useful in spatial prediction. That is to say that we cannot really measure values of any random variable. For example, air pollution, right? That is the concentration of air pollutants in space, or the crime rate in a city, groundwater levels in a region. We can't possibly be going out and sampling every single location that in a domain of interest. The domain of interest could be a ward in a city, it could be an administrative boundary like a district, a taluk, a village, a state, a country, and so on and so forth. So there are going to be many unsampled locations in space, right? For these unsampled locations, we need to be able to predict the values that remained unsampled, right? So for these unsampled locations, just because they are not sampled doesn't mean that there is no pollution. Well, there is pollution. And if we talk about environmental justice, well, people who are located nearer to areas which were not sampled have an equal right to know about the quality of air they are breathing than those areas, than those other households or people from whom the air pollution monitoring station was quite nearby. That is, they are nearer to the monitoring location. So spatial prediction is a fundamentally, social scientific exercise, right? From that perspective, right, which I just pronounced. So spatial contiguity is a concept that sort of uses stationarity of a given domain and then moves forward to then sort of provide us predictions at unsampled locations. All right. And then finally, the variogram is a device that comes from the idea of intrinsic stationarity. Another device that provides a measure for spatial contiguity apart from the variogram is the covariogram, which directly relates to the idea of second order stationarity, right? So what we saw in the previous lecture is first we were able to define the variogram and the covariogram in a statistically theoretic sense, right? And we were also sort of able to say that the variogram is a preferred device than the covariogram because it is more general, right? It holds in its definition, holds for far more general settings than the covariogram. And that goes back to the theoretical understanding that second order stationarity is strictly contained within the idea of intrinsic stationarity, right? So variogram is preferred. It's a theoretically more interesting, more general device for providing a measure of spatial contiguity in data. And once we have this measure, then we can take it forward and apply it to spatial prediction and also spatial regression, as we will see going forward. But the question is, how do we actually calculate or estimate a variogram device given a spatial sample data set, right? So the basic quest for lecture 13 is how do we calculate and estimate the variogram, right, for a given sample data set. Okay. Now, when I say calculating a variogram, I am referring to something that we will see today is called as an experimental variogram. Okay. When I say estimate, I will be talking about modeled variograms. Okay. And variogram itself is a device or measure of spatial contiguity. Okay. So, this makes pretty clear the scope of lecture 13. Okay. All right. So, let us move forward. Okay. What you have on the screen here is a textbook representation of a variogram, a covariogram and a corellogram. Okay. First of all, what is a variogram? Let's just do a little recall, a little recap of the variogram, right. So, a variogram is defined as 2 gamma h, where h is a lag vector and it is equal to the expectation of a random variable realization at location S minus the random variable realization at location, at lag vector separated by the, first location S. Okay. If we take this difference, we square it and we take its expectation. This is the theoretical definition of a variogram, right. Now, in this theoretical definition, we always have understood this definition with this figure. So, I am going to just quickly draw this figure here. You have, location S1, which I am defining as S, and a location S2, which I am defining as S plus H. Right. The vector from S1 to S2 is called as the spatial lag vector, H, right. Like I have said earlier many times that H encapsulates both distance, that is how far apart are S1 and S2 from each other, and also direction from S1 to S2, right. In a spatial data set, both distance and direction are variable, right. We do not have a convenient situation like a time series where the data are unidirectional and each hop from time period A to time period nearest time period B is equidistant, right, or the distance between two time periods is exactly the same no matter what time scale or location you are talking about. Okay. Okay. So, having understood that, the question is how do we bring this definition to a data set? Of course, if 2 gamma h is a variogram, we also saw that gamma h would be a semi-variogram. In the textbook definition, what happens is that if I start at location S and start moving from S to S plus H, which is separated by this lag vector H, right. What happens is that this device provides me a measure of spatial dependence between the two time sample points. So, if h is very small, if it is exactly equal to 0, here in this textbook variogram or textbook semi-variogram, what I see is that the variogram value is 0 or semi-variogram value is 0, right. And as we move farther away, that is as h increases, the variogram value rises. That means the smaller the variogram value, the higher the spatial dependence. At location S, if I do not move at all and take another sample point at the same time, I am going to have perfect correlation. I am going to have perfect correlation, right? Because it's just the correlation of a value by itself, right? No matter how many times I sample this point, right, I'm going to do it, I'm just creating a replica. That's why the correlation is exactly equal to 1, right? That is when the variogram value is very small, right? And as we keep moving forward, the variogram value rises. That means the spatial dependence, falls. And there comes a point when after which the variogram value will stop rising. That is the point of no correlation, the point of no spatial correlation. This point signifies that if I were to move farther out from S to a distance which is large enough, let us say h prime from S, I will learn nothing from the value that is realized at location S for predicting the value at this location S plus h prime, right? I learn nothing. This is the no spatial correlation point, right? The point at which the height from the x-axis to this large scale no correlation, no spatial correlation point signifies what is called as the sill. The sill is nothing but large scale variation in data. The distance h, which is signified here as range, right? The distance r, or when h equals r, signifies the range after which there is no spatial dependence in data. Okay, so this is a textbook variogram that we have seen earlier. This textbook variogram turns out to be a mirror image of a covariogram. What is a covariogram? Well, we saw that as well. A theoretical covariogram is the covariance between z of s and z of s plus h, right? So, if there is high spatial dependence, the covariogram value is pretty high. If at the point when spatial dependence dies, the covariance becomes 0. This is exactly what is happening with the mirror image as well, right? So, the variogram, although is a bit unusual from how we sort of study dependence of two different random variables, in traditional statistics, it is nothing sort of more complicated than a mirror image of the covariance formulation or the covariogram formulation that we are aware of, right? When we come from the covariogram to the correlogram, which is nothing but C of h divided by C of 0, remember this C of 0 is nothing, is the large scale variation in data, right? It is the large scale variation in data. It basically means that this is the covariance or the correlation of a covariance of a random variable by itself. So, covariance C of 0 is just covariance Zs by itself, right? This is nothing but the variance of Zs, and for a stationary domain this is nothing but sigma squared, which is exactly equal to sill. This is interesting, all right. So, the maximum value of a correlogram is 1. Well, that is the correlation between Zs by itself is 1, right. The covariance is not 1, but the correlation is exactly 1 because it is just C0 over C0, right, when h is equal to 0. Okay. If you want to sort of get a mathematical relationship between CH and 2 gamma h, well, what you are looking at is the following. Let me use a different ink so that it is clearer. So, we have 2 gamma h, which is nothing but the variance of Zs minus Zs plus h is equal to the variance of Zs plus the variance of Zs plus h minus 2 covariance of ZS and ZS plus H. Okay. Now, by definition, variance of ZS is C0, look here, right, plus again C0 minus 2CH. So, what we have is that gamma H is just C0 minus CH. So, gamma H and CH are inversely proportional. That is why they are simply mirror images of each other, right. So, when at the point when gamma H is 0, that is point at the origin, CH is just C0. So, this height here is C0, which is exactly same as the height of the sill. Okay. So, this sort of slide, this slide gives you a very sort of detailed understanding of what is a variogram, what does it really mean, how do we interpret a variogram, what's the intuition behind it, use our understanding of the covariance from traditional statistics, of correlation from traditional statistics. I highly encourage that you start with this, you reproduce this slide at least a couple of more times by yourself, so that you get a very clear understanding of what a variogram is, a theoretical variogram is. Okay. So, with that understanding, we will now move on to taking a step forward in order to defining a variogram for a given sample data set. For doing that, let's recall this idea of local stationarity from exploratory spatial data analysis. So, remember, in case of ESDA, right, in case of ESDA, we plotted the values, the bivariate scatter plots of values realized at any given location with their neighbors one step forward and one step backward in different directions, in directions like towards north south or east west, or both, right. And the idea of local stationarity is that these values should be similar to each other because they are located so close to each other. Now, this is also the idea of spatial contiguity, right. So, in this bivariate scatter plot, if I were to draw a 45 degree line that represents the area where Z of S is exactly equal to Z S plus H. This is the line at which correlation between ZS and ZS plus H will be exactly equal to 1, right. If all the scatter plot data sets were to lie on this line, then it will represent a condition when each data point exactly explains each other data point in its proximity. That is fantastic, because then I can just sample any one data point and exactly figure what will be the next proximate data point to this observed data point, and then keep going one step forward and reconstruct the entire domain without even sampling more than one data point, right. Well, that's not going to be the that's an idealistic situation. That's not how real data sets work, right. The real data sets work like what we see for the coal mine data that we learnt earlier. What happens with the real world data set is that for any given value, any given real world value, let's say we work with value 9. So, this is Z of S equals 9. For this value, when I go on to sort of drawing a vertical hash line, it allows me to identify the values of ZS plus H that correspond to this line. Okay. So, I have 1, 2, 3, 4, 5 proximate values to ZS equals 9. Some of these values are very, very close. Some of these are very close to ZS. They represent very strong spatial dependence. Some of them are quite far apart, quite different, right? Very close meaning not location but similar values, right? And some of them are quite distinct or or different relative to Z of S equals 9, right? It could be in the positive direction or in the negative direction. Irrespective of that, the idea is there is high dissimilarity, right? So on average, however, the data seem quite similar in their locality, right? But not exactly the same. Now, this idea of spatial dependence can then be brought forward to the variogram, right? So if if I had only one Z of S, which is a very close value, I expect the variogram value to be small, gamma h to be small, right? And if I have a distinct value from ZS equals 9 at S plus H location, right? So then I expect the gamma H value to be high, that is reflecting a lower spatial dependence value. Okay. Based on this understanding, let's try and create a an experimental variogram. That is, we will calculate a variogram value from the data. To do that, first of all, this H scatter plot or this bivariate scatter plot that we have worked with, see that it reveals correlation of data over a particular lag vector H. And we know that correlation comes from covariance, right? So C of H is it should be covariance. Sorry about this typo. It reveals covariance directly, and then correlation can be calculated as a function of covariance or correlogram, right? So it reveals covariance, and we know from our first slide that covariance and correlation are mathematically and graphically mirror images to each other. They are inversely proportional. That means if I can get the covariance measure CH from the bivariate scatter plot, I should also be able to get the variance measure from this, the variogram measure from this scatter plot, right? Because we know they are simply linearly related, right? So the bivariate scatter plot can be a very good starting point. However, remember, it is for a given value of H. So it will provide me a 2 gamma or a gamma value which is at a given lag vector H. Okay. Now, given a spatial data set or a data sample, the variogram is written as the following. It is equal to, it's given as 2 gamma H, which is by definition the variogram, is equal to 1 over some value, right, number of observations, which is denoted as modulus n in H. Summation I goes from 1 to nh, summation of first difference squared values of realizations at location S and location S plus H. This value n, capital NH, is a set. This is a set notation, and it says it contains elements I comma j in pairs. So it contains pairs of elements such that they are separated by the lag vector H. So the set n of H contains all data pairs in our sample, right? All data pairs, all unique data pairs in our sample that are, separated by lag, or let's say spatial lag, H, right? And the modulus value of H, this modulus of H is nothing but a notation for the count of unique elements in set n H. So NH is something like a neighborhood data set. It's a neighborhood set, not data set. It's a neighborhood set. So I'm going to define it as a neighborhood set, right? So it sort of collects the pairs of neighbors that are separated by a lag h, right? Neighborhood set for the spatial lag h. Now let's look at the data-based definition of 2 gamma h and the theoretical definition of 2 gamma h and try to figure out the correspondence between the two. The theoretical definition was expectation z of s minus z of s minus h squared, that is it, right. So, this expectation of the first, the difference squared. So, it is a mean squared value of, values at spatial lag h in my given data set. The expectation operator has been replaced by 1 over n summation of these, difference squared entities. That's about it. So, we are looking at the sample representation of our variogram. Okay. So, next, after learning this, we are going to go through the process of actually calculating this variogram given the above formula, right. I am going to write down the formula here again. So, 2 gamma h is 1 over number of unique elements in the neighborhood h, neighborhood set for lag h, summation I equals 1 to n of h. So, we sum through all the elements, that is all the pairs of locations that are separated by spatial lag h, summation of the difference of Si from Si plus h squared. So, I have a representation of a mean squared difference, okay, of a mean squared difference. In order to do that, in order to make our lives easy, what we do is we sort of, the starting point is, called as the tail, and the point that is separated by this tail, that is the starting point, the initial point, by a lag vector h is denoted as the head, right. So, we are starting at S1 and we are going to S2, where S2 is nothing but S1 plus h. Again, h is encapsulating both the distance as well as the direction. For the given example, what you see here is that you have a h value, let us say it equals 10, right. So, you take this tail and head representation and you collect the pair where you have ZSI and ZS plus 10. The colors on your, on this regular lattice are basically representing, data, data values, right. So, they are just digital numbers that are now embedded as a color scheme, right. So, you can note these values, you can take the first difference and then you can square it. That square enters, right here. So, this is S plus 10 and this is S. Okay. Now, just like you sort of take this device which goes from the tail to head, what you do is you take it around to every possible pair in this data set. Okay. So, what you do is, as a second step, you are going to take it onto the next, cell on the right, and you are going to collect the pair, k comma L. So, you can say this is ZSK and this is ZSK plus 10, right. The previous one was I. So, you will take this device and you will run it through every possible, sample pairs that are separated by lag vector h. Using these unique values, you will collect them in a set which will be called as the set NH, right. So, we can collect all these pairs that are separated by by the lag vector H. You can imagine there will be very many such pairs. For these pairs, we will define the lag vector, the neighborhood set NH, and with these data and the set definition, we can evaluate the experimental variogram 2 gamma for a given value of H. See that we are only looking at one H value in one direction. I can take the same H value and change the direction from east to west, or west to east rather, to north to south. That is to say that I could take the same vector and go downward from north to south and collect another a sample of location pairs that are separated by the lag vector H. Now, although H represents the same distance, H equals 10, but in a different direction. And also, nobody is actually stopping me from going diagonally in the sense of direction. So, you can imagine that you will have many values of H and many values of in the sense of direction. Similarly, I could make my H value smaller. Instead of 10, I could be working with H equals 5. So, then I will have many more sample pairs in these data. I could also equivalently work with a very large value of H. Then you can imagine that my set NH with a large value of H, let us say H equals 20, will have a lower number of entities than for N of H. So, for this regular lattice, I can actually claim that the count of elements or unique pairs that are separated by a lag of H tilde, is going to be smaller than the count with lag vector H if H tilde is greater than H. And on the other hand, this count will become larger if the lag vector I am going to look at the value, not the direction, if H tilde is less than H, right. I hope this is clear. This is just to make things clear. We are not going to use these things going forward. Okay. So, this is for a regular lattice. But what if we have an irregular lattice? And in fact, when we work with data, we usually have to work with irregular lattices. All right. So, now going forward in the next part of this lecture, we are going to study how to calculate a variogram if the data are a irregular lattice. All right. Thank you.